Dear students, today we are going to discuss topic of formation. Formation is a level surface on which the ballast is laid. The formation has to take all the loads coming on the track. The top surface of the formation is kept slightly sloping towards the sides in order to facilitate the drainage. Level of the formation is the level prepared at its center. Formation may be in fill or in cut, or partially in fill and partly in cut. When the section is in cut, the drainage becomes must. Functions of formation. It distributes the load over wider area of the natural ground. It provides smooth level surface for the placing of the ballast. It facilitates the drainage. It acts as foundation to the track and provides stability to it. So this function is very important. Widths of formation. Top widths of the formation will depend upon gauge of the track, number of tracks, center to center distance between the tracks, width of the ballast layer, width of the drain on either side if the track is in cutting. There are some important considerations regarding width of formation. Width of the formation for single line broad gauge track is 20 feet and width of the formation for double line broad gauge track is 35 feet. Well, this slide is showing the cross section of a railway track and you can see the formation, and above the formation you can see the other important components of the railway track, and this is the top view of that track. Height of formation. Height of the formation depends upon soil conditions, highest flood level, natural topography, intensity of pressure transmitted to the ground. Side slopes. Side slope of the formation must be flatter than the angle of repose of the ground. Side slopes in case of embankment is 1 vertical to 2 horizontal. Side slopes in case of cutting is 1 vertical to 1.5 horizontal or even steeper. The side is vertical when solid intact rock exists. Well, this slide is meant for the formation width for embankment, and you can see that for the broad gauge, meter gauge and the narrow gauge, the formation widths for embankments are mentioned. This slide is meant for formation width for cutting, and again you can see the broad gauge case, meter gauge and the narrow gauge case. Types of formation. Formation on fill or embankment. Formation in the shape of raised bank constructed above the surface of natural ground is embankment. The other possibility, formation in cutting, formation below the level of natural ground. So here you can see the single track case and the double track case, and this is the case where the formation is on fill. And this slide is for formation in cutting, And here again you can see the single line broad gauge track case, and this is the double line broad gauge track in cutting. Type of soil for formation. Well, there are certain requirements that must be fulfilled. No skip grading is allowed. That means gap graded material or soil should not be there. If fines in the proposed formation material are plastic, then these shall not exceed 5%. If fines are non-plastic, then can be allowed up to 12%. Uniformity coefficient in no case less than 4, preferably more than 7. Coefficient of curvature must be between 1 and 3. Well, in this case you can see the two different types of formation. You can see this one, the black color grain size distribution curve, curve A, and you can see the curve B, which is in the blue color, and the different fractions that we are having. In curve A, gravel 2%, sand 89%, and silt and clay 9%. Whereas in second case, that is the B material, gravel is 2%, sand is 93%, and silt and clay 5%. We know that sand is that material that will pass through sieve number 4 but will retain on 200 sieve. Gravel is that material that will retain on sieve number 4, and silt and clay, which are also known as the fines, are just passing number 200. So considering soil A and the soil B, soil A is not gap graded, fines are 9%, plasticity index is mentioned as non-plastic, coefficient of uniformity is 3.3, and C sub C is 1.2. Whereas in the soil B you can see it's gap graded, and the fines are 5%, plasticity index non-plastic, coefficient of uniformity 1.5, coefficient of curvature 0.98. So you can see in the both cases the fines are non-plastic, so no problem. But if you just look at the coefficients value, so you will come to know that this soil A should be preferred. Earthwork for formation. To keep the permitted gradient and to avoid too frequent changes of gradient, it is usually necessary for the level of formation to be below or above the natural ground level in different places. The natural level must therefore be lowered by cutting where it is high or raised by an embankment where it is low. In extreme cases where depth of cutting would be excessive, tunnels are made through the ground. Where an embankment is possible, the track is supported on bridges. Soil exploration and feasibility study include the following: permanent land, temporary land, formation, slopes of cutting and embankment, side drains. First, look at the permanent land. When a new railway line is planned, a tentative decision in respect of the proposed construction is made based on preliminary studies. A certain strip of land on either side of the center line of the proposed track is acquired by the railway department. The strip or land thus transferred to railway by the other department or acquired by the personal possession is termed as the permanent land. The width of the permanent land depends upon a number of things: gauge of the track, single line track or double line track, formation width, side slopes of the formation, side drains, side slopes of cutting or embankment, possibilities of further extension of track. Temporary land. In every rail project, the preparation of formation is the first stage of the execution work. An ideal condition is that the amount of material excavated from cutting is sufficient for embankment. However, when excavation and embankment do not balance, it is better to temporarily acquire a strip of land adjoining the permanent land from where earth may be borrowed. It may be utilized as the spoil bank for the excavated earth. So you can see this diagram showing the permanent land and embankment. So this one is meant for cutting, that means the permanent land in cutting. So such type of diagrams can be prepared, and in this case you can see that the drainage is very important. So you can see the side drains have been provided. Guidelines for execution of earthwork. Control of water along with the type of subgrade plays an important role in the construction of formation. So in this regard, a number of things to be considered. Non-cohesive soils like gravels and sands must be preferred, and in the case of cohesive soils, silty clay or clay soils may be there. Organic soils, peat, organic soil, silt are undesirable soils. Cemented sedimentary rocks, sandstone, limestone, metamorphic rocks, slate, igneous rocks. So there are different, you can say, possibilities. Soil exploration and surveys. Geotechnical investigations are carried out for identification and classification of soil. Boring and soil sampling are carried out from the areas where borrow pits are to be located at intervals of about 0.5 km or where change of strata occurs. In case subsoil problems are likely to be encountered, the spacing of bore holes should be reduced. Doubling of sampling should be done at locations known to be troublesome in existing track. Organic clays, silts and peat shall not be used for making of embankment. Cutting in these types of soils should be avoided. Design of rail formation. Design should be such that the track is able to sustain track geometry under anticipated traffic densities and axle loads during service under most adverse conditions of weather. It necessitates that bank or cutting is structurally stable. Settlement in the subgrade supporting soil masses are within permissible limits. There is no bearing capacity failure. Embankment soil shall attain moisture density equilibrium during weather cycles. Compaction of earthwork. The method of compaction should satisfy the conditions of economy and efficiency of earthwork. Compaction cannot guarantee the stability of formation, particularly in the following cases. excessive creep or slipping of slopes because long-term shear strength and water contents are not governed by the compaction at the time of construction. Swelling and shrinkage of soils occur during wet and dry seasons respectively because physiochemical properties of soil do not get altered by compaction. Mud pumping at ballast soil interface. Mud pumping is, you can take it like that if there is a soil and the moisture content is very high and above the formation the ballast is present, and when load is transferred through the ballast to the very soft formation, then there is a chance of mud coming in the upward direction, and that is called as the mud pumping. Settlement due to consolidation of bank and subsoil, which can occur even for a few years after construction of bank. Method of compaction. Sandy, silty soils with moderate cohesion, cohesive soils, cohesionless soils. So these are the different cases which can be considered. So compaction of sandy, silty soils with moderate cohesion. For such soils, compaction in layers by rollers is most effective. Vibratory rollers have been found more effective than the static rollers. Greater thickness of layers is allowed. Compaction of cohesive soils. The main objective of compacting clay soils is to achieve a uniform mass of soil with no voids between the chunks of clay which are placed during the earthwork. Rollers will sink into the soil at high moisture content, while chunks will not yield to rolling by rollers if moisture content is low. Sheep foot rollers are most effective in breaking the chunks and filling the large spaces. I'm sure you are familiar with the sheep foot rollers. In the case of sheep foot roller, we are having the projections upon the drum of the roller. Compaction of cohesionless soils. An effective method to compact cohesionless soil is to use vibratory rollers. Moisture content control is not necessary in the cohesionless soils. Poorly graded sands and gravels with uniformity coefficient less than 2 should not be used in earthwork for banks to safeguard against liquefaction under moving loads or due to an earthquake. Cuttings. If the subgrade soil is not fit to absorb stresses of traffic, the cutting will be made deeper to take a layer of blanket or sub-ballast of adequate thickness. In cutting of slope, softening of the soil occurs with the passage of time. Therefore, long-term stability is vital for designing of cutting. Unstable formations. Variation in the track level, particularly during extreme hot or wet season, causing the need for speed restriction or increased maintenance. Loss of ballast which sinks into the formation. Instability of bank slopes resulting in slips and consequent disruption of traffic. Causes of formation troubles. If any formation is suspected of giving any trouble, the first step should be to identify the cause of the trouble. To do so, the data regarding the ballast penetration profiles along with the history of the section and the trouble should be obtained from and must be analyzed. Following are the most common causes: instability, problems due to railway cutting or embankment not being stable, resulting in excessive deformation, excessive swelling and of shrinking of bank soil, causing large volumetric changes and thus unequal settlement and heaving of the formation, disrupting the track level and alignment. Bearing capacity failure due to inadequate formation weights or bank slopes, inadequate thickness of the ballast and the blanket. Other causes such as loss of formation soil caused by animals, ants, rats and seepage. Formation failures. The failure of the formation is due to the following: failure of natural ground under the formation, failure of the fill material in the formation, failure of the top of formation. So these are the three different cases which can be considered in this regard. So failure of natural ground causes. The failure of the natural ground takes place due to excessive settlement or the shear failure. The failure due to excessive settlement is generally associated with the upheaval of the ground beyond the toe of the embankment. The shear failure normally takes place during the construction or immediately after the construction. Now the failure of natural ground and the remedial measures: use of sand piles by using the wooden logs, counterweight at the toe by providing sand drains which help in quicker consolidation. Failure of fill material causes excessive loading which produces excessive shear stresses in soil, steepness of the slopes, percolation of rainwater. So here we will discuss the percolation of rainwater. Percolation of rainwater in the embankment increases the weight of the soil on one hand and reduces its bearing capacity and resistance to shear on the other hand. Shear failures of the existing embankment are quite common and occur by slips. The forces causing the failure are weight of the embankment and the weight of the rolling stock. The forces which resist this failure are internal friction and cohesion of soil. So failures are of different types like toe failure, base failure, slope failure. Well, in this figure you can see that if the slip circle, or you can say, is originating somewhere here through the slope, so this is called as the slope failure. And if you are having the slip surface coming through the toe, that is called as the toe failure, and this one is treated as the base failure. And here you can see the balancing embankment has been placed for the stability. Failure of the fill material remedial measures: by flattening the slopes by providing steps in the foundations, by providing stone pitching on the sides, providing proper surface and subsurface drainage, height of the embankment may be reduced. Failure of top of formation, remedial measures. Use good blanket material or sub-ballast at the top of formation. Use of geotextile fabrics. It will act as separator between the top layer and the ballast. Secondly, it will act as reinforcement to the soil and will help in better drainage. Now, at the end of this file, you would find some formation treatment methods. So various methods are used to stabilize soil embankments. Stabilization by driving piles, poles or scrap rails into the embankment of medium height. By driving sand piles in the embankment. Stabilization by pressure grouting. Stabilization of embankment soil by chemicals. Stabilization by use of geotextiles. And the other possibility is by providing an inverted filter. So in this way we can treat the formation. So that's all about the formation. Thank you.